Hello, my name is David Ackerman, and this is the thermal assembly. Let's get started. These are the given variables that were given, and these are the following assumptions that we're going to make. So the piston is a closed system. We're going to neglect kinetic energy and potential energy. We're going to assume quasi-equilibrium, and the piston exerts Carnot power. So it's also reversible. So 1 to 2 is isothermal, 2 to 3 is adiabatic, and 3 to 4 is isothermal expansion, and 4 to 1 is compression, adsorptive compression. So these is the diagram from state 1 to state 2 to state 3 to state 4, and it loops back to state 1. So for part A, we're trying to solve the heat and work for each of the process. So process 1 to 2, these are the given variables where we find from table A4. These are the variables. We find the work using this formula, and then we simplify it, plug in the variables. Work 1, 2 is 135.92 kilojoules. This is we are neglecting KE and PE because that was our assumption, and we find that the Q for process 1 to 2 is 1,200.69 kilojoules. So for process 2 to 3, these are the given variables. These is that we find out for table A4. We can find out the specific volume by using this equation. We're plugging in all the known variables. And for specific volume at state 3 is 13.66 meters cubed per kilogram. So here we're finding U3 using the exact same formula but a different variation, plugging in the variables, and we find that U3 equals 1750.84 kilojoules per kilogram. Now here again we're using this energy in minus energy out equals the energy change of the system. There's no energy change in stage 2 to 3, so we can take out and neglect that, and we can simplify it to solve for work at 2 to 3, and we find out that work from process 2 3 is 595.67 kilojoules. Process 3 to 4, now we're working in the P sat at 40 degrees is 7.3851 kPa. So the piston is at the Carnot cycle, therefore it's and reversible. So we're going to use these formulas. We're going to find that by using these formulas and plugging the variables in, the values in, and making sure that it's in Kelvin, not in Celsius. So we're going to convert those. So Q3 to 4 is 718.71 kilojoules. And now we're going to use the first law of thermodynamics yet again, neglecting KE and PE. We're going to find out that by simplifying it, plugging in our values, and simplifying it into these, plugging in our values, we're going to find out that Q3 to 4 is negative 718.51. We can find out H3 with these valuable values, X3, HG, HF on the table. We're going to use yet again another variation. Find H3 is 1,851.7 0.73 kilojoules. H4, we're going to use this formula. We're going to find H4 is 825 kilojoules. And yet again, we're going to use this exact same formula, but there may be different variations. You're going to find x4 equals 0.27 around. Now we're going to use x4 and these other variables to find u4. And then we can find now W3 to 4 is this number right here. And it's negative, so the work is actually being done into the system because the sign is negative. So for process 4 to 1, we're going to use it again, the first law of thermodynamics. Like the Q41 is 0, and neglecting KEPE, we're going to plug in all our values. We're going to get W41 equal 4 to 1 is this value. This is charting all of it, and the thermal efficiency is 0.4. We can find out the thermal efficiency by calculating the thermal efficiency here in two different methods by plugging in the work and the QH. And we're going to find out in both methods we get 40%, so around 40%, so we can assume that both are equal.